Okay. Okay, so week nine, this is the first lecture of week nine. And today we are going to be trying to understand the question of why it is that phase transitions are so hard to solve, why it took so long to solve the problem. And we're going to solve that by looking at the application of dimensional analysis to field theory. And we started doing that last time, so I just want to recap that and then do the calculation. Then I want to go back and look at dimensional analysis for correlation length, for correlation function, and remind you about the notions of scale interference that I've already introduced to you. And then we're going to start on the epsilon expansion, which is the foundation of these field theoretic methods. So we will give some discussion of that, and that's what we will be doing today. Okay, so last time, what I did was I said, let's go back and look at how we consider Landau theory. So we write down Landau theory as this intermediate level of description, and what we do is over here on the left-hand panel, we write it down as a functional integral, which you've met in the homework. We haven't formally gone through a lot of the manipulations of that, but we will do next time. And the Landau free energy is written here in the dimensional units that we constructed with up to now. So gamma is a coefficient that is related to the range of interactions. A is a number, T is T minus Tc over Tc, B is a positive number, H is the external field, and M is the coarse-grained magnetization. And what I did in last lecture, at the end, I said, let's go and put this into a canonical form. And so we defined a rescaling of the variable and of the variables. And I've shown you that rescaling here on the bottom of the left-hand panel. And when you end up doing that, then you define your effective Hamiltonian as being beta times the Landau free energy. And that now takes the form that I'm showing you over here on the right-hand panel, where the coefficient of the gradient term is just 1/2. And then there's a number R0 multiplying the quadratic term and a number U0 multiplying S to the fourth. And over here on the left-hand side, I have the scalings I think there may have been a misprint in last lecture, and I may have missed a factor of 2 in one of those things. So let's check that. Check that if you don't want to be confused. So now I want to go ahead then with the calculation. So the next thing we're going to do is so we have now that z is up to a constant factor, the integral over this degree of freedom times the effective action as a function of S. So that's what we have. And now the way we're going to do dimensional analysis is we're going to notice that because the effective Hamiltonian is in the exponent, it must be dimensionless. Okay, the exponential is a function, so it has to be a dimensionless thing. So that means that the dimensions of the effective Hamiltonian has to be 1, meaning that, in other words, since it's in the exponential, it must be dimensionless. So that's the idea. So that's the first thing. So that's what I'll call step 1. Step 2 is we're going to now look at our gradient term, and that gradient term must be dimensionless. Every term in the integral for the effective Hamiltonian must be dimensionless. So when we look at the term the integral d dr of 1/2 grad s squared. So that is part of the Hamiltonian. And so that means that the dimensions of that must also be 1. has to be dimensionless. So let's now have a look at what are the dimensions of that quantity. So this means, so remember that this term here, integral ddr, that has dimensions of length to the power d. This gradient term has dimensions of inverse length, but it's squared, so it has dimensions length to the -2. So what then we have is that this implies that L to the d times L to the -2 times then the dimensions of the field S squared must be unity. And therefore, what we learn that that the dimension of the order parameter field has then to be L to the power 1 minus d over 2. Okay, so that's the dimension of the field after I've done these changes of variables. All right, so that's a step 2. So now let's have a look at the remaining terms. So let's now have a look at the next term. So the next term is the term integral dr of r naught over 2 times s squared, and so that dimensionally has to equal 1. And so what that means is that this term over here has to be of dimensions L to the d. This term here, S squared, is L to the 1 minus d over 2, but then it's squared, so that's like that. And so then in the middle, I have the dimensions of R naught, which I don't know, and that has to all equal 1. So in that case then, what we have is that the dimensions of R naught have to be, so I've got I have L to the d, and then I have L to the minus d, and then I have L to the -2. And so we have that the dimensions of R naught are L to the -2. Okay, so R naught, the coefficient of S squared, has to be an inverse length. And so what we would expect, let's see if that makes sense. So what we expect is that what is the length? The characteristic length scale should be the correlation length psi of t. And we know that in mean field theory, which is what Landau theory is, in mean field theory, we know that psi of t scales like t to the -1/2. And so what that means is that then R naught should then be proportional to L to the -2, and therefore should be proportional to t. In other words, t minus tc over tc. And that exactly makes sense, because when we started off doing this, over here we have in our Landau free energy that we had a t times m squared. That's how we derived the Landau free energy many weeks ago. And so so this dimensional analysis has correctly told us that the coefficient of the order parameter squared is proportional to t, and basically goes like 1 over the correlation length squared. So that is indeed consistent. So I can just say that this is consistent with our phenomenological derivation of Landau theory. Okay, so that's that term. So now we've got one more term to do. So now we're on to step 4. And in step 4, what we're going to evaluate is the last term. The last term is the integral of ddr, and then we have u naught over 4 times s to the fourth, and that thing has to equal 1. Okay, so let's go ahead and see what that is. So that says then that the first term is going to be, this term is length to the power d. The next term is the dimension of u naught itself. And then this term, s to the fourth, so that is going to be L to the power 1 minus d over 2, all raised to the power 4, and that has to be dimensionless. And so that then tells us that u naught has dimensions of length to the power d minus 4. Okay. Now, the characteristic length scale associated with the phase transition is the correlation length. So using as our characteristic length scale, L is equal to the correlation length. So that is then T to the minus 1/2 in mean field theory. We already know that. And so that means then that U naught scales like T to the power minus 4 minus D over 2. Okay, and this is a very important result because it says let's for example take the case where say D is equal to 3, and that says that U naught scales like T to the minus 4 minus 3 is 1, so minus 1/2, and that is happening as T tends to 0. So in other words, what we've just discovered, the most surprising thing is that for D less than 4, as T tends to TC, the U naught diverges. And U naught is the coefficient, is the strength of the nonlinear coupling of the order parameter with itself. And so what that means then is that as D is less than 4, U naught goes to infinity. And so whereas you might have thought that we could do perturbation theory, in other words, we could it dooms perturbation theory, and we'll see why in a second. Why does it doom perturbation theory? Well, you might say that you might say, well, if we look at the terms a half grad s squared plus 1/2 r naught s squared, that is just a free field theory. It is you can diagonalize that and compute the partition exactly. So this could be your unperturbed Hamiltonian. And then if that's the case, then that means that the term U naught over 4 s to the fourth integral ddr, that would be the perturbation. But what we've learned is that as t goes towards tc, or as little t goes to 0, U naught diverges to infinity. And so this perturbation term is not small near the transition. So it's very, very weird, right? This is strange. it's strange because T minus TC over TC is a small parameter, but it's not usable. When we try to do perturbation theory, the perturbation parameter is diverging. And so perturbation theory will not converge, and nothing you know how to do will work. That's why this problem is so hard. Okay. In fact, the turbulence problem is the same thing. Very good question.
Yeah, if there's a net should be you're not supposed to as t to the minus g minus 4 because correlation length goes as t to the minus 1/2 and g is held to t minus 4.
Hopefully not. Oh,
Then everything you said is true for t equals 5.
no. There's a typo somewhere. There is a typo. You're totally right.
It should be replaced with L. U not as L power.
Yeah, why? Let me just check here.
Oh, yes, u not goes as 4 minus t, not t minus 4. That would be right.
Say it again.
I think u not goes, oh. No.
Let me check. Let's see, what did I do wrong here? Okay, I know how to. I should fix this. There is a I'm going to have to fix this later. I can tell you, I think this is correct. L is, if you put t to the minus 1/2 in here, and you get t to the minus 1/2, t to the minus 1/2 times d minus 4. Yeah, the problem, yeah, I did it too quickly.
There's just one mistake. I mean, it should be t power 4 minus d over 2. That's it. There's no extra negative sign.
Yeah. That's
Yeah, but no, but I did make a mistake, and it's because I made it. I did this too quickly. I'm going to go back. I'm going to rewind. Okay. I think I did make a mistake here. I didn't present it correctly. So here's why. Here's what I did. That was, I think, not where I went too quickly. So thanks for raising the question. So it is confusing. Let me explain what I want to do next. Okay, what I did too quickly was I went from what was the unperturbed Hamiltonian to the I didn't take out the scaling of that. So let me rewind. Okay, so there's a mistake in what I wrote. Okay, so here it's done correctly in my book, but in my notes I did it too quickly and I skipped a step, and I skipped a step that's important. Okay, so So remember what we have is our effective Hamiltonian is this. It's the integral ddr of 1/2 grad phi squared plus 1/2 r naught phi squared plus 1/4 u naught phi to the fourth. Okay, so that is what that's what we've just derived. So now what we're going to do is so I missed out a step, and it's an important step. So apologies for missing this out. Okay, so so this step 5 is this. What we want to do is we want to get this into the form of h is equal to some h naught plus some h interaction. So this is going to be our unperturbed Hamiltonian. Which we can solve exactly. And then this is going to be the one that is we treat by perturbation theory. Okay, so this is the thing that I missed out. So what we're going to do is I'm going to define another rescaling. So I'm going to say here we've got the physical dimensions of space. So we know that so we're going to rescale space in units of L, i.e. the correlation length. So I'm going to define X to be R over L. And then I'm going to define a new field, phi, which is going to be the original, this field. Man, I'm making so many typos today. I'm sorry about this. Let me fix this here. Okay. I used the wrong notation and it's going to confuse you. So let me do this again. Grad S squared plus 1/2 R naught S squared plus 1/4 U naught S to the fourth. So that's what we already derived. So I'm going to define a new field, phi, which is the original field divided by L to the power 1 minus D over 2. Remember that we've chosen the dimensions of these quantities, we've calculated them, so we can write explicitly a Hamiltonian that is dimensionless. So that means I want to get the spatial degrees of freedom out, and I know everything in terms of spatial degrees of freedom. So once I rescale space in terms of my units of space, which in this case is going to be L, the correlation length, then I have to define the L is going to be R naught to the minus 1/2, and U naught, I'm going to find a new field U naught, which is the original field U naught. We know its dimensions are length to the power D minus 4. Okay, so now if I make this change of variables, now I've truly got the thing in dimensionless form. So my partition function now depends on one variable, which is this U naught bar, and it's going to look like this. Integral d phi, this new field, e to the minus h naught of phi minus h interaction of phi. So it's going to depend like that. And h naught is now going to be integral, because I've counted out all the factors of space, the length scales and so on. Everything now is dimensionless. So this is 1/2 grad phi squared plus 1/2 phi squared. So all the coefficients in my unperturbed Hamiltonian are just pure numbers. There's nothing that depends on t minus tc. And then my interaction Hamiltonian, that then looks like this, integral d dx, and then 1/4 u naught bar over phi to the fourth. So that's what the interaction Hamiltonian looks like. So if I then ask, what is this u naught bar? So the partition function now only depends, there's only one parameter in this whole problem. That's the effective quartic coupling term. The quadratic terms are all exactly solvable, but the quartic term is not, and the only parameter that the partition function depends on is u naught bar. And u naught bar is, if I follow the definitions, it's the original u naught times r naught to the power d minus 4 over 2. And now when I write that down, that means it goes like some u naught times a power t to the power d minus 4 over 2 times a coefficient which I called a tilde of d minus 4 over 2. So this is the only quantity that the thing depends on. Now, when we do perturbation theory, what do we mean by that? So what we mean is we take the partition function and we write it as e to the minus h naught, and then we expand the exponential of the interaction Hamiltonian. So it looks like this: 1 minus h interactions plus 1/2 h interactions squared, ... That's what perturbation theory is. It just means expanding the Hamiltonian. So this part we can calculate exactly because it's just a quadratic Hamiltonian. And so that means it's just a Gaussian integral. And then these parts here are the perturbation. But the problem is that as t tends to 0, this u naught bar, this redefined quantity, that thing goes like t to the power d minus 4 over 2, and that diverges as t tends to 0, or as capital T tends to tc. And so the small parameter is not small. And that's the problem. So what that means is that for d less than 4, perturbation theory is bad. And for d greater than 4, then perturbation theory converges, or at least the perturbation parameter is indeed small. That doesn't actually necessarily mean that perturbation theory converges, okay? Because I can have a series of terms where the terms are all getting smaller and smaller, but the series actually diverges. So that can happen too. So the fact that the parameter is small is not a necessary and sufficient condition for the theory to be convergent. So, but certainly if the perturbation parameter is large, then it's then it's not at all obvious that it converges, at least in finite order of perturbation theory. So that's the reason why this is a better a better way of saying it than this. What I wrote here is not correct. Okay. So hopefully I got this right, and I copied it down right, and I got the equations right. So happy? Okay. Thanks for catching my mistake. Okay. All right. So that's why things are bad. So let me just add this comment that I made just now in passing, because I think it's an important one, and I want to summarize it so that everybody gets it. So here's my so the summary is that we want to do perturbation theory. Want to do perturbation theory about the simple, exactly solvable integral h naught. That's what we want to do. But in the correct dimensionless units, where we are using the scalings of the zeroth order perturbation theory, the interaction terms are large as the temperature tends to the critical point. And so that means that you can't do perturbation theory. And that's why we have to do something smarter. Okay, now, in other words, what I've shown you is that if you look at these terms in perturbation theory, and I now look on the left-hand panel, these terms here, what I've shown you is that these terms diverge as t tends to tc. So in other words, what I've shown you is that the individual terms in this perturbation theory diverge as t tends to tc. And this divergence of terms of perturbation theory was the thing that got everybody excited when they were doing when quantum field theory was invented. This is the thing that Feynman, Tominaga, and Schwinger won the Nobel Prize for, because when people tried to understand quantum mechanics of the electromagnetic field interacting with matter, what people discovered was that the terms in perturbation theory, even though you have the fine structure constant being a small number, 1/137, when you do perturbation theory, you find that the individual terms in the perturbation theory are divergent. And the thing that Feynman, Tominaga, and Schwinger won the Nobel Prize for was inventing this process of renormalization, which absorbed the singularities that gave rise to the divergences into a reparameterization of the terms in perturbation theory, a redefinition of the constant. Okay, so when we call this process that I've taught you renormalization group, the renormalization part of that is the same renormalization as you get in quantum field theory. It is the removal of infinite terms in perturbation theory. Now, so now let me tell you another. So this what I've just told you is this is the connection between renormalization group and renormalization in quantum field theory. So technically, the problem that we're having at phase transitions is the same mathematical problem that we have in quantum field theory. Okay. Now I want to make an additional comment. Okay, so so you might say, well, what does it mean having terms diverge in perturbation theory? So it doesn't actually mean that the perturbation theory makes no sense. So here is a very subtle comment. Just because the individual terms in perturbation theory diverge, it doesn't mean that the perturbation theory itself diverges. Okay, let me explain what I mean. Okay, so the perturbation theory, when I say about perturbation theory, I mean this formula here on the left-hand panel, sums to all orders. Now, just because the individual terms diverge doesn't mean that when I sum them, I get something that is divergent. So let me give you an example of that. Let's suppose I give you a thing that is this minus t raised to the power n over n factorial, and that is n equals 0 to infinity. Okay, and I'm going to look at this thing as t goes to infinity. Okay, so I'm going to sum that series. Okay, so if you look at each term in that series, each term diverges. Agreed? T goes from infinity. Each term diverges. But what does the whole thing do when I sum it? Okay, so let me just write this down. So each term diverges, but question, does the sum itself diverge? And the answer is it's just the exponential. The answer, so the answer is, does it diverge? No. So what does it converge to? Yes. So the series, the summed series, goes to e to the minus t. And so therefore, e to the minus t as t goes to infinity is equal to 0, which is perfectly finite, perfectly good answer. So all of this problem of divergences in perturbation theory, it's a very, very subtle issue, because you can have a divergent series, but you can sum it and get a finite answer. So I'm not going to go through the mathematics of that, but one of the ways that you can evaluate critical exponents and so on is you can actually say, well, okay, I can sum divergent series and get finite answers. So let's just do that. So another way to do critical exponents is to look at all these divergences and use techniques to sum all of them in ways that you can justify in a principled way and get finite results that way. So there's a very deep mathematical connection between asymptotics of series and so on, then and what we're doing in field theory. Okay, so I think that's what I want to say about that. There are some other comments. Oh, well, let me make another comment. Actually, since I'm talking about this, let me make another comment, because it's also quite interesting. Okay, so here's another comment. All right, let's look at d greater than 4. Okay, in d greater than 4, you might say, well, all the terms in perturbation theory all the terms of perturbation theory are finite and get small as t tends to Tc. So you might say, great, so the sum of the perturbation theory is going to be finite. That's not true either. Okay, so it's not true. So the question is, does that mean that perturbation theory is finite for d greater than 4? Okay. Does it converge? Who thinks yes? It's plausible that it would, right? Because these terms are getting smaller, you might say it's a convergent series. Okay, it's not true. Okay, so the answer is this the smallness of the expansion parameter is not a sufficient condition for the convergence of perturbation theory. Okay, so you might say, well, okay, that's fine, that's just a mathematical nicety, but let me prove to you that it actually has physical significance. Okay, so let me explain why. And this argument is an argument that was originally due to Freeman-Dyson. So it's called Dyson's argument. And let me explain what that is. So Dyson's argument says, I've got the partition function as a function of my rescaled interaction parameter U naught bar. So I have this sole parameter that tells me what is the strength of the interactions between the fluctuations that we neglected in mean field theory. What is the strength of that compared to that? And so my partition function, as we know, is the integral d phi, and then it looks like this, integral d dx. Then there's a quadratic part, a half grad phi squared plus a half phi squared. So there's no coefficients in there. And then I have minus, I'm getting the important part in running into the margin. So let me write it down here, times e to the minus the integral d dx, this u naught bar parameter times phi to the fourth. So that's what the partition function looks like. Okay, then let's suppose I say, let's have a look at what the partition function looks like when I put a minus sign in front of the quartic term. So if I do that, then what I get is the integral over phi, e to the minus the integral d dx, a half grad phi squared plus 1/2 phi squared. That's my unperturbed Hamiltonian. And then now it's multiplied by e to the plus the magnitude of u naught times the integral d dx of phi to the fourth. And you can see that this term here is now very divergent because this is positive, and so this means that the integral, the functional integral for z naught, will diverge. So when I change the sign of the interactions, I get a convergent integral when it's one value, and a divergent integral when it's a negative value. And so what that tells you is that implies that u naught bar equals 0 is a singular point of the partition function. And that implies that the radius of convergence of any perturbation theory is 0. And so because of that, that means that if I'm doing a perturbation theory, it can't be convergent. The best it can be is asymptotic. And this is why in quantum field theory, when people do Feynman diagram calculations, you do them up to a certain order in perturbation theory. And as you go to higher and higher orders of perturbation theory, the calculation stops working as well. And this is what happens in quantum electrodynamics. It turns out that if you go to, I don't know, 10 decimal places, whatever order of perturbation theory that is, 8th order or something, it works fine. You get very good accuracy. If you go to higher order in that, then the calculation starts to diverge. And so the fact that it actually works so well is actually a little bit of luck to do with asymptotic series. Okay, so this has all been very, very esoteric, what I've just told you, but it's an important aspect of why this problem was so hard, why quantum field theory was so hard, why phase transitions were so hard, why the people who solved these problems got the Nobel Prize. As I told you before, Ken Wilson's point about the normalization group was this is the renormalization group process is fundamentally non-perturbative. So the whole thing about Feynman diagrams and perturbation theory using field theory, all of this stuff here that two of you like, okay, it's important. Those of you who are going to be theorists, you do have to learn that stuff because it is part of the techniques of theoretical physics. However, Feynman diagrams do not solve problems for you. The most powerful methods are not using those types of methods. Okay, I'm going to now I'll take questions if anybody has any questions about what I've said, and then I'm going to go and switch gears. I'm now going to give you the basic idea of how we do the field theoretic version of the normalization group, and doing expansions in non-integer dimensions. So does anybody have any questions about this very, very obscure, very esoteric, advanced topic that I just very, very briefly skated over just to let you know that they exist? You have a question?
RG explain why we consider only the 3 terms that we have in the exponent. We neglected 5 power 6, 5 power 8, all of those.
Yes, RG does explain that.
Oh.
Because and that's actually a homework exercise. Okay, I'll try to talk about that on Thursday. But RG explains that because those terms are irrelevant.
The same irrelevant as we discussed last time.
Yes, yes. So if you look at this Gaussian fixed point, if you look at the non-perturbed Hamiltonian, so you're looking at your Gaussian fixed point over here, looking on the left-hand panel. If you go and then work out what are the relevant terms there, the 5/4 term is the relevant one. 5/6 is irrelevant. Okay, and all the high ones. So yes, fantastic point. The normalization group does explain how it is that you can neglect all these other terms and you still get exactly the right answer. Okay. Now, there are phase transitions where the 5/6 terms do matter, and those are called tricritical points. Okay, we're not going to have time to go through that. So there are certain sorts of phase transitions where there's 2 parameters that you have to tune to get to the transition, not just 3 parameters, I suppose, not just the external field and the temperature, but also the pressure. And that happens, for example, in helium-3, helium-4 mixtures. There's a homework exercise on that in my book. I'm not going to ask you guys to do it, but so there are phase transitions where that happens. It also describes the types of polymers, for example, so as well. So it depends on the problem, how how far in these expansions you need to go. And different problems have different structure. Okay. So let's go on to the next topic. So I want to talk now, at least at some level, the basic idea of a field theoretic renormalization group. So this is, oh, actually, you know what? I don't want to do this now. I remembered that I want to change. No, this is fine. This is fine. We'll do this. So what I want to explain now is in my book. This is now the beginning of chapter 12. So this is chapter 9 and also chapter 12.1. Okay. Okay. So I want to go through some introduction to that. We don't have enough time in the class to go into this in huge amounts of detail, but I want to try to explain the important points. So what we're going to do is our goal here is expose the basic ideas, not go too far down the rabbit hole of technique. And so that's our goal. And so what is the basic idea? So let's go back to our real space renormalization group. So the real space renormalization group that we did a week or so ago, we saw that was quite cumbersome, quite laborsome. We had to generate all these terms. We had to develop lots of irrelevant variables, and then even that we had to keep track of them, but they didn't contribute to the final answer. So our real space renormalization group had the problem that we ended up calculating many irrelevant terms in the effective Hamiltonian. And so what we would like to have is a more streamlined way to get the results. So what we're going to do is we're going to, so the basic idea is don't use real space. What we're going to do is use Fourier space. And what we're going to do is we're going to eliminate short distance behavior and the way we're going to do that is we're going to call our cutoff lambda. So note that before we had lambda defined in real space. But I don't want I don't want to write 2 pi over lambda everywhere. So where I used lambda before in real space, now I'm going to use 2 pi, which will in k space be 2 pi over lambda. I'm now going to define our cutoff lambda to be in momentum space, in k space. Okay, so that's something that is different, all right? Okay. All right, so we're going to do that, and so what we're going to do is we're going to integrate out Fourier components with k greater than lambda. So these are going to be the short distance components. And then the analog of block spins will be the effective long wavelength, i.e. small k Fourier components. So basically what I'm saying is, before we had a coarse-grained order parameter on the scale of lambda, and that's now going to be replaced by its Fourier transform. So it's going to be like this, and then we're going to look at components where naught is less than k is less than the cutoff, and then those ones we're going to keep, and then the ones where k is greater than lambda, those ones we are going to eliminate, integrate out. And these ones we're going to keep. So that's the basic idea. And what is our analog of block spins? So what we're going to do is we're going to, after you've integrated out modes with k greater than lambda, then what we're going to do is rescale length by a factor of L. And that means that basically the scales that we remove are lambda over L is less than K is less than lambda. So what we're going to be doing is integrating out shells in momentum space. And that's the basic analog of doing block spinning. So let me draw you a picture. So the way I want you to think about it is like this. I'm going to draw a horizontal axis. This is going to be k, the wave vector. We're going to define fields from naught up to some scale lambda, like so. And what we want to do is we want to keep the long wavelength parts and integrate out the short wavelength parts. So I'm going to define a scale here, which is lambda over L. So L is like the block spin size. And then these here, these are the high wave number modes. And so I'm going to think of those I'm going to think of those as being like the variables sigma that we had before. And then the modes that are over here, these are the long wavelength modes. And those will be like the block spin variables, which we call SL prime. So all the way of breaking the degrees of freedom up into long and short wavelength modes that we did in real space, we can do in momentum space as well. And so that is how the process is formally done. Now, next time I'm going to come back to a little bit more about how we do that. What I want to explain now in the last, well, let's see, I reckon we have 3 minutes left. Let me just tell you about the basic idea then. Okay, so then let me carry on with the basic idea. So the basic idea is our starting theory, our starting effective Hamiltonian depends on two parameters, R naught and U naught in unscaled units. And so what you might expect is that when we do RG, then we will get a renormalization group flow for R and U. So we're going to get something like that, and in principle higher order terms as well, but those turn out to be irrelevant. So let me just say also coupling constants for phi to the 6, phi to the 8, and so on. But these are irrelevant. At the Gaussian unperturbed renormalization group fixed point, which I'll show you next time. So we don't need to compute those. So we just need to compute the quartic ones. And the basic idea from Wilson and Fisher is expand in a fake small parameter which is called epsilon, which is defined to be 4 minus d. And we're going to pretend that that parameter is small, and then at the end of the day, set epsilon equal to 1, if we want to do 3 dimensions. So the procedure is expand as if epsilon was much less than 1. And then once you've done that, then we set epsilon equals 1 to get d equals 3 results. And how you justify that is by resummation methods called a Borel summation and so on, where you can take these asymptotic expansions and get finite results from that. So the justification is a lot of Borel summation and asymptotic analysis. And I'm not going to go through that. So that is the procedure. And this sort of field theory approach to renormalization group does this. We're going to go through a little bit superficial aspects of it next time. We're not going to go through into all the technical details. Okay, so I think I'm going to finish here. So we'll get some more into that next time. So let me turn off Zoom, and I can take